Hello and welcome back, y'all. This is our last lesson in polar curves and polar area. And last time we spent some time figuring out the area enclosed by a polar curve. But you don't always have just one polar curve. Sometimes you have multiple polar graphs, and we're going to find the area between them. Example 1. Find the area of the region that lies inside the circle, 3 sine theta, and outside the cardioid, 1 plus sine theta. Well, let's figure out what's what first. This is the circle. That's 3 sine theta. And then the cardioid is this guy down here. So we want inside the circle and outside the cardioid. So that is that region right there. Well, how do we do that? Step 1 is going to find the intersection between the two curves. So we'll set them equal to each other and solve, and we can see that they intersect at pi over 6 and 5 pi over 6. So let's go ahead and write that on there. Now, to find the area between the curves, well, let's set up an expression for area. Now, just between those two lines of intersection, we need the area that's inside the circle, inside the whole circle, and then we want to subtract this that's inside the cardioid. See that? So that's what our expression is going to look like. We've got the circle on the outside, and we'll subtract the cardioid. And the formula is pretty much the same as it was last time, right? We've got 1/2 and then r squared d theta. It's just that we have 2r squareds that we're working with this time. And of course, we're integrating between the places where they intersect. So once you've got this set up, well, now you just have to plug in what is the circle? What is the cardioid? And then at the end, use your trusty calculator and you get an area of 3.14159. You recognize that? So fun. Example 2, find the area of the region that lies inside 3 sine theta and outside 2 minus sine theta. That's the one below there. So what region would that be? Right there? It just looks like a snowman to me. Anyway, like we did before, the first thing we've got to figure out is where the graphs intersect. So set them equal to each other and solve. And again, we've got pi over 6 and 5 pi over 6. And again, like we did before, we can just take the whole of 3 sine theta and subtract 2 minus sine theta. And we're doing that between pi over 6 and 5 pi over 6. And then use your trusty calculator to solve it. Now this one gets a little bit trickier, of course. Find the common area. This is the area that they share of 4 sine theta, so that's the circle up here, and r equals 2. So that's the circle down here. Now I can't just take one and subtract the other, because when I subtract the other, then I take out their common area, right? So we have to think about this a little bit differently. So like we did before, let's find the intersection. Oh geez. Okay, so the intersections are not always pi over 6 and 5 pi over 6. They just happen to be in these examples. And let's draw the boundaries there. And then if you'll notice, between 0 and pi over 6, the only thing that's involved is 4 sine theta. And between 5 pi over 6 and pi, the only thing that's involved is 4 sine theta again. Between the two, The only thing that's involved in this middle section is r equals 2. So that's what we're going to use to set up our integrals here. So I'm going to color just the stuff that's 4 sine theta gray, and just the stuff that's r equals 2, we'll color that green. And then we're just going to find each of these pieces separately. So the first gray part goes from 0 to pi over 6. And of course, we've got 1/2 r squared d theta, but it only involves 4 sine theta. Then the second part only involves r equals 2, and that goes from pi over 6 to 5 pi over 6. And then the last part goes from 5 pi over 6 to pi, and we're back to just using the 4 sine theta again. And you use your calculator to solve that one. Now this last one, this was one of the AP questions in 2018. The graph of the polar curves r equals 4. See, I always like to stop and just figure out what the heck I'm looking at. So this is r equals 4. And 3 plus 2 cosine theta, it's right here, are shown in the figure. The curves intersect at pi over 3 and 5 pi over 3. Yay! They told us the intersections. Let R be the shaded region that's inside the graph of r equals 4 and also outside the graph of 3 plus 2 cosine theta, as shown in the figure. Write an expression involving an integral for the area of R. Well, we know how to do that. We already have the 2 intersection points. And then if it's this just outside area, then we'll take the outside one, that's the circle, and subtract this, inside part that we don't want. And we'll use their intersections, pi over 3 to 5 pi over 3. And we just have to write an expression. We don't have to solve it. So we will go on to part B. Find the slope of the line tangent to the graph of r equals 3 plus 2 cosine theta at theta equals pi over 2. Now notice, the line tangent, we are now introducing a rectangular form. So the line is going to pop out of polar and into rectangular form. So in order to find the slope of that, we have to take dy d theta over dx d theta. But what's y and what's x? Well, y equals r sine theta. Here's r and then sine theta. Remember, y equals r sine theta. And x equals r cosine theta. So here's my r and cosine theta. And if I've remembered that, now it's just a matter of, well, taking the derivative of both of those. So the first thing I'm going to do is distribute the sine through. Then take the derivative, and looks like right here we'll have to use the product rule. And then let's do the same for x. We'll distribute the cosine through, and then take the derivative. Now, dy dx is the y prime over the x prime. And then we have to evaluate that at pi over 2. So plug in pi over 2 to all of that. You get some unit circle practice. And you get a slope of a tangent that is 2/3. Part C. A particle moves along the portion of the curve r equals 3 plus 2 cosine theta between 0 and pi over 2. The particle moves in such a way that the distance between the particle and the origin increases at a constant rate of 3 units per second. Find the rate at which the angle theta changes with respect to time. We've got some related rates here. At the instant when the position of the particle corresponds to pi over 3, and of course indicate units of measure. Okay, so what do we know? We know from inside the problem, they told us that dr d theta is 3. And what we want to find is d theta dt at pi over 3. We also know what r is. R is 3 plus 2 cosine theta. So now we can take the derivative of that, and we get dr dt equals negative 2 sine theta d theta dt. So from here, we know dr d theta is 3, and we want to know what's happening at pi over 3. So sine of pi over 3 is root 3 over 2, and then we can just solve for d theta dt. The last part asked us to indicate units of measure. So in this case, that would be radians per second, and we're done. That wraps up our unit on parametric and polar. I will see you for the next unit.